My name is Zeki Erkin. I'm from Delft University of Technology and I will be chairing this session. We have so far 5 speakers available, so we are still missing one. So hopefully we will get that person on time. But the first speaker is with you. Are you ready for your presentation? Okay, then the floor is yours, but expect some people interrupting slowly.
Sure. I'll try with the mic.
This one is fun.
Okay. Yeah, I hope you can hear me well. So hello everyone, people. So today is my pleasure to present our recent work, FedLAP, and this is a joint work with my amazing colleagues, Ralph and also Mario. So let's first begin with some background. So as you already know, deep learning has sort of revolutionized the world. We already have a lot of interesting applications like segmentation, or ChatGPT, or even diffusion models for image generation, or even video generation. But this all comes at a cost. For example, the demands on computation resources has been significantly increasing in the past around 10 years, and it's even faster than the Moore's law. And moreover, the amount of required training data set is also increasing exponentially. So I would say this kind of bottleneck needs to be considered for the future applications. So as a remedy, federated learning proposed by Google a few years ago enables users to jointly train a model without sharing their data with each other. So typically, this framework is realized by the following steps. First, the clients can first train their models locally using their private data for a few local steps, and then they only share the gradients with the central server. So as long as the server receives the gradients, they can use it to, for example, taking average over the received gradients and then update the global model. And they just broadcast the updated model back to the clients and repeat this process until, for example, the model converges. While it sounds quite promising and actually has been implemented in many real-world applications, it actually is still facing a lot of challenges. One of the most critical ones is optimization over non-ID data and also differential privacy. So this kind of non-ID data would typically yield inconsistent objective functions and also deviating gradients. Alright, sorry for the technical issue. So basically, this non-ID optimization problem can be briefly described by this equation. So we can see here, as long as you optimize your local models on your local private data for a few local steps, the resulting gradients will be different from the global gradients, which, for example, if you gather all the data together and then directly optimize the model. And this is simply because the local objective function is consistent with the global one. And to give you an illustration, for example, you have 2 clients. Each of them has either, say, old cat or dog images. And then if you train model on these clients and then simply take averages over them, then you might result in, I don't know, in the middle of nowhere instead of the desired cat-dog classifiers. So, and furthermore, if you want to introduce more theoretical privacy protection like DP, you will further amplify such deviating gradients and makes the problem even worse. So to mitigate this challenge, we let's first take a closer look at this equation. So the problem comes from the inconsistency between the objective functions. So if we can find an approximation to replace this bias loss function, then with such an approximation, we can sort of convert the problem back to centralized learning. And so in this work, we try to propose novel optimization methods that can find a proper approximation. And then in the meantime, we also want to retain privacy protection, and also we don't want to introduce additional communication costs. The idea is that since the gradients could be biased because of the biased local data set, we try to communicate local loss landscape. And the idea is that we can actually synthesize a small set of images that will deliver gradients that is similar to the one generated by real images. And after, so in each communication round, the clients just send these images to the central server. And once the central server receives these synthetic images, they can train the model as in centralized learning. So with such strategy, we can avoid bias optimization caused by the non-IID data or gradients DPSGD. I won't go into the mathematical details about how we achieve optimization, but basically, we first of all we need to measure the gradient similarity between the one generated by synthetic images and also the real images. And since we don't want to introduce additional communication cost, we can only maintain a small set of images. So in this way, in this scenario, we only approximate a small neighborhood, which is measured by the distance between the updated models and also the initialization. And lastly, in each communication round, we also do sort of meta updates to mimic the optimization on the server side. And then we just communicate such synthetic images. And once the server receives that, they just do things like you do in centralized learning, but following the radius or neighborhood you define on clients. And then to further integrate theoretical privacy protection like DP, we simply need to replace the real gradients part. We first use DPSGD, use DP algorithms to sanitize real gradients, and then we just follow the same procedure as we described before. And due to a nice property of DP, post-processing theorem, we can show that any downstream optimization won't breach the protection, which means that the generated images can be freely shared anywhere, and any potential privacy leakage will be upper bounded by the privacy budget you set at the first place. So in the experiments, we test our method on 3 common benchmarks, and also we consider 5 clients, and each one has 2 disjoint classes out of total 10 classes, which would result in a very extremely non-IID case. And we also consider a few common baselines, which are kind of state-of-the-art for in FL. And then for DP settings, we just apply DP-SGD to these baselines. So let's first begin with the non-DP experiment. You can see here, first of all, our methods performs quite well, outperforms the baselines, or just comparable to the baseline, but incurred require a similar level of communication costs. And another interesting point is that we found that our method typically learns faster and more stable compared to the baselines, which probably can be attributed to this non-biased optimization. And we move on to DP settings, where we consider epsilon between 2 and 10. This range is kind of widely considered in industry. For example, from Google, in some Google or Apple's product, they consider this range. And then we see that for most of the cases, our method outperforms the baselines, and especially under tighter privacy budget, our method is performs much better than the baselines. And to verify the privacy protection property, we also conduct membership inference attack against all of the baseline and also our method. So first of all, we see that it's not surprising that with DP, both gradient sharing methods or our method are quite robust against membership inference. But more surprisingly, in even non-DP method, our method seems to be also more robust than gradient sharing method. And this can be potentially attributed to post-processing theorem because we add one more step to distill the training information. So in summary, we propose an interesting novel optimization method that mitigates non-IID data optimization. In the meantime, we also provide is still compatible with DP and provide theoretical privacy protection. And then we can remain a similar level of communication cost. And yeah, so in the experiments, our methods performs quite well. But lastly, we hope our work can sort of motivate the community to think about or investigate more novel optimizations for FL problems instead of just sharing gradients. So that's it. Thanks for your attention. If you are interested, you can refer to our paper and also GitHub code.
Perfectly on time, so even with that delay. Do we have any questions from the audience? Yes.
Hi, thanks for the great talk. I was wondering, how are you generating the samples on the client that you then send to the server? Are you just using like a GAN that gets random noise as the input during the generation?
So first of all, in this case, we don't really need realistic images. So in this case, we simply use backpropagation to learn to update the images. So to be more specific, we can start from initialize these synthetic images with real images, or simply from random Gaussian noise, and then we just use Gaussian backpropagation to update the images according to these objective functions.
Okay, thank you.
I see another question here, please.
But I take to use some information only available at the client to make these images. You can't just send the gradient to the server and let the server drive synthetic images. So what information from the client goes into this?
Do you mean the optimization part or the radius part? Or?
The generation of these synthetic images that you send to the server. If I didn't misunderstand it completely.
So you mean what kind of information I send to the server in the end, or?
Yeah.
Okay.
Yeah.
So first of all, we will send the synthetic images because from this. Because our goal is as long as you have this set of synthetic images, you can derive gradients from this set of images. And so in this case, you just need to send these images to the central server. But in non-DP case, you can also, so for both DP and non-DP case, you can also set a radius, which can be kind of hyperparameters. You can, so both server and clients can communicate at the beginning, even before the training started. So in the end, two kind of information.
I think I need to stop here so that we can move on to the second speaker. Is it okay if you continue during the coffee break?
Yeah, so if
Great.
you have any question, I'm happy to answer during the coffee break.
Great. Thank you very much for your presentation.